Hello everyone, welcome to TriTea. Today we're going to solve two interesting problems, step by step. So let's begin with the first one.
Welcome to today's explainer. So, you're trying to wrap your head around object-oriented programming in Python, right? Well, you are in exactly the right place. Today, we're going to tackle one of Python's most notorious hurdles and, hopefully, transform it into your greatest superpower. We are talking about custom objects, classes, and the true engine that brings them all to life, the constructor. Get ready, because we're about to master the blueprint of objects. If you've spent literally any time looking at Python code, you've probably seen it, that strange little word self just popping up everywhere inside classes, making what should be simple code look frankly incredibly intimidating. Let me just validate your frustration right out of the gate. This is a shared trauma for almost every Python beginner. You see these weird functions with double underscores and this random self parameter, and it just looks completely alien. But I promise you, by the end of this explainer, you're going to see exactly why it's there, and you'll realize it's actually an elegant, incredibly logical masterpiece.
Okay, let's dive right into this. Up until now, you've likely relied heavily on Python's built-in data types. When you write something simple like x equals 5, Python grabs its built-in blueprint for an integer and hands you a standard integer object. You use strings, you use lists, and they work great. But what happens when the real world gets a bit too complex for a simple string or a list? What if you need to represent a student, a bank account, or, I don't know, a starship? Built-in types just aren't enough when you want to group complex details perfectly. We need the power to invent our own custom structures.
And to invent a custom type, we use a class. A class is, quite simply, a programming tool that lets you invent your own custom data types. Think of it as a blueprint or a mold. And this is an absolutely crucial point. A class does not hold real data itself. I mean, an architectural blueprint of a house doesn't have actual physical furniture inside it, right? The class simply defines what variables, which we call attributes, and what functions, which we call methods, your custom data type is going to have once it's eventually created.
To really cement this idea, I love using this visual analogy. Think of a class as a cookie cutter. The cookie cutter itself is just made of metal or plastic. You obviously can't eat it, has zero flavor, it is strictly a shape definition. It just dictates the boundaries and the structure of what is going to be made.
Now, when you press that cookie cutter into real dough, you create an actual edible cookie. In Python, that real cookie is what we call an object or an instance. You can literally make 100 cookies from a single cookie cutter. Each of those 100 cookies sits in its own distinct physical space on the baking sheet, but they all share the exact same starting shape because they came from the same mold. So the class is the cutter and the object is the cookie.
All right, moving on to section 1, the birth station, also known as init.
Which brings us to a really fascinating question. How do we customize these blank cookies the exact millisecond they're stamped out? If you want one cookie to have chocolate chips, another to have sprinkles, and a third to just have icing, you need a way to customize them the exact moment they are born. In Python, we use what's called a constructor, written with double underscores, often called a dunder method. Init simply stands for initialization. Think of it as your automatic setup assistant that runs immediately when an object is created. And here is the golden rule. You almost never call this function manually in your code.
Instead, something pretty amazing happens. The exact millisecond you tell Python to create a new object from a class, Python secretly pauses behind the scenes. It sweeps a completely blank space in your computer's RAM, preparing a fresh memory block. Then, without you ever typing a command for it, Python jumps straight inside that init function to assign your starting data directly to that specific block of memory. It's basically a completely automated birth sequence.
Now for section 2, unmasking the confusing self. Now, what's really interesting here is how we address the elephant in the room, self. I promise you, its job makes total sense. The self variable is simply a reference to the specific object that's just been created from the class. It provides a clever way to make variables and objects available everywhere within that class. Let's ground this with one more analogy to make it crystal clear.
Imagine a massive factory line building smartphones. The blueprint dictates that every single phone needs a unique serial number printed on it. So, when a specific phone shell rolls down the assembly line, the robotic arm swings down with the laser printer. But wait, how does the robot know which exact physical phone to print on right now? There might be thousands of phones in the factory. The robot needs a target tag for the specific one currently sitting right in front of it. In Python, self is exactly that target tag. It represents the specific object currently being born. When you write code like self.name equals input underscore name, you are giving Python incredibly specific instructions. You're saying, hey, take the name string passed into our factory, find the unique object currently on the assembly line, which is self, and attach this name variable directly to its physical memory hull. It's just a routing tag.
Let's move to section 3 and see how this builds with the invisible execution trace.
Let's trace the exact flow when you execute a line of code like S1 equals student, passing in Alex and 95. Step 1, memory allocation. Python grabs a brand new empty memory address in RAM. Let's just say address 7701. Step 2, the secret handshake. Python automatically triggers the init birth station. Step 3, passing coordinates. Python passes that RAM address, 7701, straight into the self parameter. It passes Alex into the input name and 95 into the input grade. Finally, step 4, binding data. Inside init, Python goes to address 7701, creates those variables, and locks in the data.
And honestly, this is exactly why we need self. If you run the factory line again by typing R2 equals student, passing in Bella and 88, Python does the exact same process. But this time, self becomes a completely different memory address, say 9904. This perfect isolation is why Alex's grade of 95 doesn't accidentally overwrite Bella's grade of 88. Self ensures that every single time we initialize an object, the data is glued securely to the correct memory block.
Which brings us to our final section, grouping details perfectly.
So why do we go through all this trouble with blueprints and init stations and self-tags? Well, it all comes down to grouping common details perfectly. Take a look at this vehicle class structure. By using an init constructor, we can bundle complex, real-world attributes cleanly inside a single structured object. A vehicle isn't just a string or a random number, right? It's a cohesive unit. It has a year, a model, a plate number, and a current speed. The constructor guarantees that the moment a vehicle object is created, it possesses all these vital attributes immediately. Nothing is forgotten. The structure is perfect, and your code becomes a truly accurate reflection of reality.
You now understand the mechanics under the hood. You know that a class is just a blueprint, the init function is the automated birth station, and self is simply the target tag routing data to the right place in memory. By mastering constructors, you've leveled up from just using the basic tools Python provides to actually inventing your own. You have the power to logically structure any complex data you can possibly imagine. So, my final question to you is this. Now that you control the blueprint, what world will you build? Keep experimenting, keep coding, and I'll see you in the next explainer.
Programming logic is a universal language. Whether you write in C, Java, or Python, the underlying architecture of a solution is exactly the same, only the syntax changes. Take a classic challenge, the academic merit list. You have a group of students, and for each one, you need to track their name and 3 separate subject marks to calculate an official rank. If you try to track this data using separate arrays, one for names, one for math scores, one for physics scores, you create chaos. Every time you sort or move a student's rank, you have to perfectly synchronize multiple disjointed lists. To solve this, you have to pack those disparate pieces of data together into a single, unified custom data type. 5 steps build our merit list. First, define a custom student object. Second, calculate the internal metric, the total percentage. Third, store these objects in an array. Fourth, sort that array descending by percentage. Fifth, print the ranked list. Step 4 is where beginners often get stuck. When sorting, the code looks at a specific internal attribute, the percentage, to make a decision. But the sorting action itself must physically move the entire student object. Let's run a sorting pass. Slot 0 holds Alex at 80%, and slot 1 holds Bella at 93.3%. The logic checks if Alex's percentage is lower. Since it is, the code triggers a swap, physically trading the entire student data blocks. Isolating one attribute for evaluation while moving the whole object in memory is the mechanic that prevents mismatched names and grades. We can prove this universality by applying the exact same algorithm to a completely different scenario.
Now let's see how the code looks in C. in Java. In Python. Let's now move to the second one.
Tournament ranking system, where players are ranked by wins and draws. The exact same 5 steps apply. We just swap out the variables. Take a second to think about the merit list. Based on that example, how would you set up the math and the sorting condition for this new player object? Instead of a grade percentage, the math becomes wins multiplied by 3 plus draws multiplied by 1, and the sorting condition evaluates that total score. If player A has a score of 5 and player B has a score of 10, the logic evaluates those attributes. Player A's score is lower, so the entire player blocks swap places. Mastering this single logical framework equips you to build any ranked list or leaderboard, regardless of the context. While the sorting logic is identical everywhere, the way different programming languages birth these objects into memory is distinct. This textbook excerpt defines the C struct. A struct is a passive data container. You manually reserve memory on the stack, and any logic manipulating that data happens outside the structure. Java and Python work differently. They use constructors, specialized blocks of code that automatically initialize data on the heap the millisecond the object is created. But despite this shift between the stack and heap, the sorting algorithm we built remains untouched. The logic remains the same, only the form changes. Focus your practice on mastering these underlying structures, and the syntax will follow.
Now let's see how the code looks in C. Java. In Python. Comparing all three languages, C, Java, and Python, we can clearly see how the core logic is same in each three. Just syntax is the one which changes.
Tournament ranking.
Thank you for watching. See you in the next video.
Subscribe now.